In this video, we'll talk about the relationship between differentiability and continuity. There's an important connection between these two facts we've talked about for functions so far. We have continuous functions, we have differentiable functions, and there's some sort of overlap in how those are set up. So what happens here? What's the intuition? Well, the sort of thought here is if I have a function that's not continuous, so a function, say I've got here, and I have a jump, and I go off this way, and say this here happens at point A, how am I going to define a tangent line to the graph at A? Well, this seems sort of hard to do, right? I might be able to define a tangent line down here, but then I'm ignoring the whole part of the graph that approaches A up here. And because I'm looking at limits, I have to care about points that are on both sides of A and close to A, so I would care about points that are up here, but the tangent line that I draw down here doesn't really accommodate those. If I draw a tangent line up here, I'm taking care of those points, but I've ignored all the ones down on the bottom. So there's really no way to do this if I have a jump discontinuity at a point. And the same argument sort of goes for any discontinuity at a point, right? If I have oscillation or we're going to infinity, I can't really define a tangent line there because I'm ignoring points that are on one side of this discontinuity. For removables, if I move the point A somewhere else or get rid of it entirely, then my f of A isn't even defined to put it into the derivative formula. But so the point here is, this gives us a thought that maybe you have to be continuous in order to be differentiable. And it turns out this is exactly the case. However, mathematicians like to phrase things a little bit differently, so the statement looks a little different than this, but the idea is exactly this. The theorem we get from this is that if f is differentiable at a point C, then it must be continuous at that point C. i.e., if f is differentiable, then it must be continuous. And in math logic, those two statements are the same. If I have to be continuous to be differentiable, that means if I'm differentiable, I must have been continuous in the first place. So how do we work this out in terms of some sort of a proof? What does it mean to be differentiable? Well, if f is differentiable at C, then this limit, h goes to 0, f of c plus h minus f of c over h, exists and equals f prime at the point C. That's what it means to be differentiable. So the fact that limit h goes to 0, f of c plus h minus f of c over h equals f prime at C means that if I were to look at the limit as h goes to 0, f of c plus h minus f of c, just getting rid of the h down here, this is the same thing as the limit as h goes to 0 of h times f prime of c. Because h is not 0, so I can multiply both sides by it and really put things in the appropriate way to get this to work. But now, f prime of c is a number. It's a fixed number that I can find because f is differentiable. So that means this limit here is 0, giving me that the limit as h goes to 0, f of c plus h minus f of c equals 0, and that's equivalent to f being continuous at C. It means that limit as h goes to 0, f of c plus h must equal f of c. If I replace this c plus h by some x and shift things around, this is the limit as x goes to c of f of x. So the fact that my function is differentiable forces it to be continuous. You can also flip this around, saying if I know that a function is not continuous, then it can be differentiable. In particular, functions are not differentiable at asymptotes, at jump discontinuities, things like that, because the function is not continuous at those points. Let's see the relationship between differentiability and continuity. Remember that it only goes one way. If I am differentiable, then I am continuous. There are examples, namely things like f of x equals absolute value of x that we saw before, that are continuous, but not differentiable at certain points. But that's the idea of how these properties relate to each other and how you can use them to sort of analyze functions and know if they're differentiable or continuous based on how they are defined.